So today I'm going to be talking about simple logistic regression, which is a method of statistical analysis used by epidemiologists to answer questions such as are the odds of a heart attack higher in males compared to females, or do the odds of a heart attack increase as body fat percentage increases? And what these questions have in common is the outcome is binary. It happens or it doesn't. You have a heart attack or you don't. Just quick refresher about what we're talking about here. So regression is a way of representing the relationship between an exposure and an outcome. So the thing causing the disease. Um, and yeah, just a quick review of the anatomy of a line. So y equals mx plus b, it's your classic grade 9 line formula. So y is the outcome value, m is the slope, rise over run. Here it comes out to 1. X is the x value at a given place in the function, and b is the intercept, which is always the same. So for example, if we say x of 3, we can get the y value by plugging in 3 into that formula. So 3 times 1 plus 1, so we can see that it's 4. So this is a function that represents our line here. In epidemiology, we kind of frame things a bit differently. We call the intercept b naught, and we call the slope b1. And that's the part that is most interesting because that's what tells us, that's how we get an odds ratio, basically. And in another video, I'm hoping to show how we derive an odds ratio, but you'll just have to take my word for it for this video. So like I said before, with simple logistic regression, you have a binary outcome. You're disease positive or disease negative. It happens or it doesn't. And your exposure can be either continuous, like age, or categorical, just like the outcome, where it has a finite number of options. So because our outcome is something that happens or it doesn't, our y equals mx plus b formula, the y would be the probability of the event happening given what we know about the exposure. And the actual formula for a probability sucks. Like it isn't a line here. It's not just y equals mx plus b, and the function isn't a line either. So forget that. Basically, we just use the logit instead because it puts it onto a linear scale, and now we have mx plus b is our formula, and it's a line, and that's just much better. So a logit is a log odds. So here we have probability of the outcome over probability of the non-outcome, so probability of it happening over probability of it not happening. And that's the definition of an odds. And we just call that a logit. That's the short form. So as far as interpreting those parameters, I'm going to start by talking about when the exposure is binary. So like our question before, the odds of a heart attack, are they higher in males than females? We typically assign a value of 0 and 1 to the two levels of our variables. So our two levels are female and male. Whatever we call 0 is the referent, and it's pretty arbitrary. Here I'm just going to put 0 for female and 1 for male. And the way our data would look like for like data that is ripe to be have logistic regression applied to it is data like this, where we have our subjects, the outcome value, and the value of sex. So for subject 1, here in this case, it's conventional to have 1 as outcome positive and 0 as outcome negative. So subject 1 is someone who had a heart attack who is female, and subject 2 is someone who did not have a heart attack who is male. And yeah, you can see where I'm going with that. So as far as interpreting the various parts of this line, well, to start with, you would input this data into SAS or some other software like Stata or R, and you would essentially, like, I'm not going to go over this, but you would give it the information it needs to create a logistic regression line from your data, and it would spit out values for this. It would have values. So how we'd interpret those is this intercept here is the log odds of a heart attack in the referent category, so females. And beta 1 here, that's the money coefficient, that's the important one. And that's the log odds of disease in males relative to females. and that can be exponentiated to the odds ratio, which is a really important measure of effect in epidemiology. And I'm hoping to do a video on how to derive why that's the odds ratio in logistic regression, but I'm going to do that in another video. But as far as why these two things, or why this applies to the males and this applies to the females, I can show that pretty easily. So um, we called x 0 when it's female. So if we plug 0 into this equation, we're left with this value representing the probability of the outcome among females. When it's males, or I shouldn't have said it's the log odds of the outcome more specifically. And when it's male, we have this function representing the log odds of the outcome when you're male, and that doesn't really have a lot of interpretability. The log odds of one thing, it's the odds ratio that's a lot more useful to us. And I'll get to that in a second. So this is just an example where if we put our data into SAS and it spit back these results, how would we interpret them? So we have 0.69 as the intercept and 1.4 is the coefficient. So here we have logit y, so it's also or log odds. So if we take the log of both sides, we have log here and we have log here as well, because we're not just odds, it's log odds. So this is log applies to this as well. To get it back on the scale we want it, we exponentiate it, because that's how you put a log back on a regular scale. And that would come out to 2. So the odds of a heart attack, the odds of a heart attack in females is 2, and that has no real interpretable meaning on its own. 1.4, that value has much more meaning, and if we exponentiate that, we get an odds ratio of 4. So that basically means that the odds of heart attack is 4 times greater among males than females, and this is just totally made up. I just chose these numbers so it would come out to a nice round odds ratio. That doesn't really mean anything as far as like the actual what the odds ratio is. So now if we have a continuous predictor, here's just I just redid the data where now it's body fat percentage from 0 to 100. So subject 1 is a male with body fat percentage of 14. I don't know what normal values are for that. Subject 2 is someone who didn't have a heart attack with body fat percentage of 18. Yeah. So just talking about the different parts of this equation, just like I did before. Now this is the intercept represents the log odds of a heart attack at a body fat percentage of 0. It's the lowest possible value of this continuous exposure, and that has no biological interpretation. You can do things like centering. If you look up a different video on centering, that'll tell you how to change the referent to something that is more biologically interpretable. And this B1 here is the log odds of a heart attack at body fat X, so whatever value of X relative to 0. And that'll be a bit more clear when I have my example. So using similar numbers, just 0.05 is the only difference here. So exponentiating that, we get an odds of heart attack at body fat 0 of 1.05, which has no real meaning. But if we exponentiate this, the coefficient, we get 2. So that basically is telling us that for every 1 unit increase in body fat percentage, the odds of heart attack doubles. And something I just wanted to mention quickly is that if this was negative 0.69, then that exponentiated is 0.5, and that can be tricky to interpret as an odds ratio sometimes. So I find it helpful to write it out like this, where an odds ratio is odds and exposure positive over odds and exposure negative, and that's equal to 0.5 or 1 over 2. So that makes it a bit more clear that those who are exposure negative are 2 times more likely, or the odds are double compared to before, when it was those that are outcome positive are 2 times more likely.